So the storyline moves from the forces reshaping manufacturing to the operating choices required to scale the modern plant. The context includes why cost, resilience, speed, talent, and carbon pressure are changing the mandate. The architecture includes how digital thread, data, connectivity, and cyber foundation create the backbone of modern technology. Technologies include where robotics, AI, twins, additive quality systems, and maintenance tools create value. The operating model include what people, governance, production systems, and safety disciplines must change. And the roadmap includes how to prioritize use cases, fund scale up, measure impact, and avoid pilot stagnation. So the modern manufacturing is shifting from automation to adaptation. The next frontier is ability to sense, decide, and respond before volatility spreads through plants, suppliers, and customers. We will see about asset efficiency. Legacy factories optimized local equipment, use stable schedules, and periodic improvement cycles. System responsiveness include modern plants, absorb demand swings, material disruption, quality events, and labor scarcity without losing flow. Learning loops include connected data, AI, robotics, digital twins, and the empowered teams, which turn operations into an adaptive system. Modern manufacturing connects product, process, plant, and people. It includes connected product and process engineering, sensor-rich plants, reliable controls and connectivity, automation, robotics, AI, quality, and maintenance systems. The boundary terms included are smart manufacturing, Industry 4, advanced manufacturing, digital operations, and Industry 5 overlap around better information flow. So we will now see about the forces changing manufacturing competitiveness, which is chapter 1. Modern manufacturing is being pulled by volatility, technology, labor scarcity, geopolitical risk, and sustainability economics. The 5 forces are raising the bar for factory performance. They are volatility and resilience. The demand swings, material shortages, logistics shocks, and supplier risk require faster sensing and replanning. The second one is technology and acceleration. AI, robotics, edge data, cloud platforms, and digital twins are moving from pilot experiments to operating tools. The next one is labor and sustainability. Skills scarcity, safety expectations, energy cost, traceability, and carbon pressure reshape the factory mandate. The competitive agenda now balances cost, resilience, and learning speed. Manufacturing performance should be evaluated as a portfolio of linked outcomes, not a single isolated KPI. Cost without fragility. Lower unit cost by removing variability, scrap, downtime, rework, and energy loss rather than blindly reducing buffers. Resilience without chaos. Use visibility, modularity, scenario planning, and qualified alternates so planners can respond quickly. Learning without delay. Shorten the loop from signal to root cause to countermeasure through connected data and daily management. Value creation is moving from plant islands to network orchestration. The factory still matters, but the winning unit of analysis is the end-to-end network. Designed to make product data, simulation, manufacturability, tooling, and process plans must travel cleanly into production. Second one is sources to deliver. Supplier visibility, logistics, warehouse execution, scheduling, and customer promise management saves service. Used to improve warranty, field, quality, and service signals should feed back into design materials and process changes. next one is maturity model. Manufacturing maturity moves through 5 repeatable states. Maturity is a sequence of data readiness, process discipline, and operating adoption. Stabilize and connect. Standard network, loss trace, reliable assets, missing data, traceability, and integrated systems create a baseline. Optimize and adapt. Analytics, predictive maintenance, quality loops, modular lines, and rapid reconfiguration improve responsiveness. Autonomize with control. Human supervised agents recommend, simulate, and execute bounded actions only after guardrails are mature. Lean remains the operating discipline. Digital changes the cadence. Digital maturity without disciplined problem solving creates dashboards that watch waste. Lean without data leaves speed on the table. Standard work. Digital instructions, guided checks, and electronic records make the expected condition easier to see. Daily management. Real-time losses and escalations shorten the time from abnormal condition to countermeasure. Continuous improvement. Analytics help teams quantify loss, test changes, and spread what work across similar assets. Evidence snapshot. Current signals show smart manufacturing has moved into scale up. Budgets are material. Deloitte reported many manufacturing executives expected significant improvement spending to go towards smart manufacturing. Robotics keeps scaling. IFR report 2024 is the second highest year for industrial robot installations, with the growth expected in 2026 and 27. Skills are being mapped. NIST Manufacturing USA links advanced occupations to technology specific knowledge and skill areas. Demand and mix. Demand volatility is changing the economics of flexibility. More variant, shorter lead time expectation, and unstable forecasts make fixed high volume assumptions less reliable. Mix volatility. Variant proliferation increases changeovers, material presentation, complexity, and quality risk at the line. Planning latency. Slow planning cycles create scheduled churn, expediting overtime, and hidden inventory buffers. Flexible response. Modern factories use modular cells, digital instructions, and rapid replanning to protect flow. Supply resilience is becoming a manufacturing design requirement. Resilience improves when product sourcing, inventory, and production choices are considered together. Qualified alternates. Materials, tooling, suppliers, and the process parameters need controlled substitutes before disruption happens. Visibility and traceability. Supplier risk, in-transit inventory, genealogy, and lot status help planners decide earlier. Design for resilience. Modern products and standardized parts reduce single source exposure and simplify recovery paths. Labor scarcity makes productivity and capability inseparable. Work redesign. Remove non-value tasks, walking, searching, manual recording, and unsafe motions before automating the remainder. Capability acceleration. Digital work instructions, skills matrices, and simulation-based training shorten time to proficiency. Human machine teaming. Robotics, vision, and decision support should augment judgment while improving safety and consistency. The smart factory architecture that makes scale possible. Modern plants need a layered backbone, assets, connectivity, data, applications, governance, and cyber controls. A smart factory is a layered operating architecture, not a single system. Assets and controls. Machines, sensors, robots, PLCs, SCADA, historians, and safety systems create the physical signal layer. Data and applications. MES, QMS, CMMS, APS, WMS, and analytics turn signals into executable production decisions. Governance and cyber. Common standards, reference architectures, access controls, and monitoring make the stack repeatable. The digital thread connects engineering intent to factory execution. The thread turns product requirements, process plans, quality rules, and production records into a traceable lifecycle system. Design definition. BOM, CAD, specifications, tolerance, and change records provide the authoritative product baseline. Process definition. Routing, work instructions, tooling, inspection plans, and control plans translate design into factory execution. Production evidence. Load genealogy, parameters, test results, deviations, and service feedback close the loop for improvement. Purdue and ISA 95 remain useful maps for digital operations. They help separate real-time control, manufacturing execution, and enterprise planning concerns. Control zone. PLCs, drives, sensors, SCADA, and safety systems require deterministic behavior and strict change control. Operation zone. MES, historians, quality, maintenance, scheduling, and warehouse systems coordinate production work. Enterprise zone. ERP, PLM, CRM, finance, and supply chain planning set demand, product, and commercial priorities. The industrial data layer turns machine signals into decision context. Raw sensor streams need models, metadata, lineage, and context before they can support operations decisions. Capture. Collect time series, events, alarms, parameters, inspections, batch records, and operator inputs readily. Contextualize. Link signals to asset hierarchy, product, lot, work order, receipt, operator, and shift. Serve. Provide governed data sets to dashboards, AI models, digital twins, MES, QMS, and maintenance systems. Edge and cloud should be assigned by latency, resilience, and governance. Modern manufacturing stacks usually need both local responsiveness and enterprise scale analytics. Keep at edge. Safety control, low latency inspection, buffering, local dashboards, and offline continuity belong close to assets. Move to cloud. Model training, fleet benchmarking, historical analytics, collaboration, and cross-plant data products scale centrally. Manage the seam. Define synchronization, versioning, recovery, access rights, and failover patterns before deployment. Execution layer. MES and MOM become the transaction layer of the smart factory. The execution layer translates plans into work and turns production evidence into trusted records. Dispatch and control. Release orders, route work, enforce receipts, sequence operations, and manage exceptions in real time. Record and trace. Capture genealogy, consumption, labor, equipment, parameters, deviations, and quality results. Integrate and improve. Connect ERP, PLM, QMS, maintenance, warehouse, and analytics into one execution rhythm. Interoperability. Interoperability events from becoming digital cul-de-sacs. Common semantics. Define asset hierarchy, units, events, products, lots, states, and reasons consistently across plants. Open integration. Use APIs, message brokers, OPC, UA, MQTT, and structured integration patterns where appropriate. Lifecycle ownership. Assign owners for interface changes, regression testing, versioning, and documentation. Cyber by design. Cyber security must be designed into OT modernization from the restart. The more connected the plant becomes, the more critical segmentation, identify, monitoring, and recovery become. Segment and control. Separate zones, restrict remote access, harden endpoints, and manage privileged accounts deliberately. Monitor and respond. Detect anomalous OT behavior, inventory assets, patch with operational discipline, and rehearse incident response. Recover production. Backup receipts, PLC logic, configurations, historians, and critical work instructions for plant recovery. Data governance. Data governance decides whether analytics scales or fragments. Governance is the operating system for definitions, ownership, access, lineage, and data quality. Define ownership. Assign stewards for products, assets, materials, receipts, parameters, quality rules, and reason codes. Standardize definitions. Agree on OEE losses, downtime reasons, scrap codes, states, yields, genealogy, and units of measure. Monitor quality. Track missing values, time alignment, duplicate tags, state master data, and metadata completeness. The third chapter is connectivity and data foundations for the connected plant. It includes reliable sensing, contextualized data, and disciplined analytics operations, which are the prerequisites for smart manufacturing scale. Instrumentation should target decisions, not collect signals indiscriminately. A good sensing plan starts from the decision being improved, quality, uptime, energy, safety, or flow. Decision first. Define the action, owner, timing, and required confidence before adding sensors or tags. Measure the right state. Capture asset condition, process parameters, environmental factors, product state, or material movement as needed. Maintain the signal. Calibrate, secure, document, and monitor sensors so the data remains trusted over time. Machine data. Historians remain critical even as lakehouses and AI mature. Time series records are essential for root cause, model training, regulatory evidence, and performance baselines. Capture fidelity. Sampling, compression, timestamp accuracy, and tag health determine whether signals are fit for purpose. Operational context. Historians become more valuable when tied to asset, product, lot, shift, and event context. Enterprise reuse. Replicating selected data to governed platforms enables benchmarking and AI without destabilizing controls. Master data. Master data quality is a hidden constraint on smart manufacturing. Products, assets, materials, suppliers, and processes need stable identifiers and relationships. Product and material. BOMS, routings, receipts, alternates, packaging, and specifications need controlled versioning. Asset and process. Asset hierarchy, work centers, capabilities, cycle standards, tooling, and constraints need common definitions. People and permissions. Skills, certifications, role, and access rights should align with actual work and compliance needs. OT and IT networks must converge without erasing their differences. Connected operations require collaboration between control engineers, plant leadership, cybersecurity, and enterprise IT. Shared architecture. Defined zones, conduits, remote access, wireless, edge compute, and enterprise connectivity together. Different risk logic. OT prioritizes safety and uptime. IT prioritizes confidentiality, standardization, and rapid patching. Joint operating model. Create shared change windows, asset inventory, incident response, and lifecycle funding. Event-driven architecture helps the factory react in operational time. Production events should move across systems quickly enough to trigger the next best action. Trigger. Events should include downtime, quality holds, material shortages, parameter drift, order changes, and safety alerts. Route. Message brokers and APIs route events to MES, QMS, CMMS, APS, dashboards, and human workflows. Act. Rules, alerts, automations, and escalation paths convert event data into timely response. Data quality. Data quality problems compound quickly in connected operations. A bad signal can trigger wrong actions faster when systems are integrated and automated. Common failure modes: missing tags, state master data, inconsistent units, clock drift, duplicate assets, and manual entry errors. Operational impact: false downtime, incorrect yields, unreliable genealogy, poor scheduling, and mistrusted dashboards. Control approach: create data qualify rules, owners, monitoring, and remediation loops inside daily management. Contextualization is where most manufacturing data work becomes valuable. Asset context: line, cell, station, equipment, component, control, module, and maintenance history. Production context: work order, LOT, SKU, recipe, material batch, operator, shift, and cycle state. Business context: customer priority, service risk, cost impact, regulatory requirement, and improvement owner. Analytics operations. Analytics operations keeps models useful after the pilot ends. Plant conditions, materials, recipes, and maintenance state change. Models must be managed accordingly. Deploy responsibly. Define model owner, decision boundary, human review, escalation path, and rollback method. Monitor drift. Track input quality, prediction accuracy, false positives, false negatives, and operative override patterns. Improve continuously. Use feedback loops, retraining, validation, and governance to keep models aligned with operations. IIoT economics should be framed around value pools and reuse. Connectivity is not free. Value comes when common patterns are reused across assets and sites. Value pools prioritize downtime, scrap, energy, labor, yield, quality escapes, and inventory decisions. Cost drivers: sensors, gateways, licenses, network, and cybersecurity integration, validation, and support all matter. Reuse logic: create repeatable reference designs, data models, dashboards, and deployment playbooks. Chapter 4 is automation, robotics, and flexible production systems. Modern automation should improve flow, safety, quality, and labor productivity without creating brittle factories. Robotics adoption is broadening from fixed cells to flexible systems. The robotics portfolio should match task variability, safety needs, payload, precision, and integration complexity. Industrial robots, high speed, high payload, repetitive tasks such as welding, painting, palletizing, and machine tending. Collaborative robots, lower force, shared space tasks where flexibility, setup speed, and worker interaction matter. Mobile automation, AMRs, AGVs, and automated handling improve material flow and reduce non-value movement. Collaborative robots. Cobots work best when the task is stable enough and the work cell is redesigned. The value comes from the combined human-machine workflow, not simply placing a robot next to an operator. Good fit, light assembly, dispensing, inspection support, kitting, machine tending, screw driving, and repetitive handling. Design needs, fixtures, part presentation, grippers, safety assessment, tag balance, and operator standard work. Adoption risk, unstable upstream processes, poor ergonomics, and unclear ownership can make cobots underperform. Mobile automation. AMRs and AGVs convert material movement into a managed flow system. Flow design, map routes, pickup points, line-side supermarkets, replenishment triggers, and traffic intersections. System integration, connect WMS, MES, scanners, fleet software, elevators, doors, and safety systems. Operational discipline, manage mission priorities, downtime recovery, maintenance, battery health, and manual override rules. Flexible automation is the response to high mix and shorter life cycles. When products change faster, automation must be reconfigurable rather than built only for a single stable SKU. Modular cells use reusable stations, mobile fixtures, standard utilities, and parameterized recipes. Fast changeover, digitize setting, automate checks, mistake proofs tooling, and stage materials before the switch. Common interfaces, standard controls, data models, tooling interfaces, and safety patterns reduce integration burden. Machine vision moves quality control closer to the process. Use cases, presence checks, dimensional checks, surface detects, label verification, assembly validation, and safety monitoring. Design factors, lighting, camera placement, part presentation, image storage, model validation, and false reject strategy. Closed loop value. The highest value comes when vision data adjusts process conditions or triggers rapid containment. Control modernization must be balanced innovation with upstream discipline. Risk inventory, assets, hardware, age, spare availability, unsupported firmware, network exposure, and undocumented logic. Migration path, use staged cutovers, simulation backups, and rollback plans to protect uptime. Human-machine interfaces should reduce cognitive load at the line. So abnormality. Make status, alarms, interlocks, trends, and next actions visible without dashboard clutter. Support standard work. Use guided workflows, checks, visualites, and confirmations where errors are costly. Design for escalation. Escalation paths, context, and ownership assignment should be visible when help is needed. Safety and ergonomics should be built into automation choices. Hazard reduction. Remove people from repetitive lifting, sharp tools, heat chemicals, confined spaces, and traffic exposure. Ergonomic design. Optimize reach, height, weight, posture, visual load, and part presentation for human work. Safety life cycle. Risk assessments, guarding, interlocks, validation, and training must evolve with automation changes. Automation business cases should capture system-wide value. The strongest cases connect automation to bottleneck relief, defect prevention, safety, and service reliability. Direct value, labor productivity, throughput, changeover, cycle time, uptime, and utilization improvements. Risk value, safety, stalling risk, quality escapes, regulatory exposure, and process consistency improvements. Life cycle cost, integration, maintenance, tooling, training, spares, cyber software, and future product changes. AI, analytics, and digital twins as design engines form our chapter 5. Advanced analytics matter when they improve prediction, simulation, optimization, and daily decision quality. AI creates value when embedded into a defined operating decision. Predict, forecast failures, quality drift, schedule risk, demand shocks, material shortages, and energy peaks. Recommend, suggest parameters, maintenance actions, reschedules, root causes, containment, or operator guidance. Predictive maintenance shifts the question from failure to risk. Condition based on predictive approaches prioritize work before failures damage production flow. Signals, vibration, temperature, current, pressure, acoustic, lubricant, alarms, and process performance data. Decision, prioritize intervention timing, spares, labor, downtime windows, and production risk trade-offs. Quality analytics can prevent defects before inspection catches them. Early warning, detect drift, correlations, abnormal patterns, and changing defect risk before final inspection. Root cause, link defects to lot, machine, tool, receipt, shift, material batch, and process conditions. Control response, trigger containment, parameter adjustment, maintenance training, or supplier alert. Scheduling optimization links factory constraints to customer commitments. Advanced scheduling must model capacity material changeovers, labor tooling, and service trade-offs. Constraint visibility, represent bottlenecks, calendars, qualification rules, WIP, material availability, and sequence constraints. Digital twins vary by purpose, fidelity, and operating cadence. A useful twin represents the right part of the reality and the resolution required for a decision. Asset twin models conditions, degradation settings, maintenance history, and operating envelope for equipment. Process twin models parameters, material behavior, quality outcomes, energy, and throughput dynamics. Simulation lets manufacturers test changes before disrupting the line. Simulation is most useful when it reduces cost, risk, or time of experimentation. Layout and flow. Test bottlenecks, WIP, routes, labor, conveyors, storage, and line balance before physical moves. Process parameters, evaluate settings, tolerances, recipes, energy, yield, and quality trade-offs. Generative AI. Generative AI is useful when grounded in plant knowledge and workflows. Gen AI can help retrieve, summarize, draft, and guide work when it is connected to trusted manufacturing context. Knowledge assistant. Retrieve SOPs, maintenance manuals, troubleshooting guides, quality standards, and training content. Autonomous agents should start with bounded supervised action domains. Recommended first, start with prioritization, root cause suggestions, schedule options, and maintenance recommendations. Constraint actions, use approval gates, parameter limits, safe states, audit trails, and rollback procedures. AI governance is a manufacturing safety and reliability requirement. Validate before use. Test models against known cases, edge conditions, process changes, and failure modes before operational use. Control access. Restrict who can change models, prompts, data sources, parameters, and automated actions. Chapter 6 refers to advanced materials and additive manufacturing. Additive manufacturing shifts value from tooling to data controlled geometry. The economics differ from subtractive and formative process because complexity is often penalized by tooling. Best fit uses. Complex geometries, lightweight structures, space paths, custom medical devices, tooling, and low volume protection. Digital inputs, CAD, build files, machine parameters, powder or material history, and process monitoring become critical records. Additive success requires design, qualification, and post-processing discipline. Design for additive. Topology, lattice structures, consolidation, support strategy, orientation, and surface requirements matter. Qualify the process. Machine, material, parameter set, operator, inspection, and environment must be well dated for the application. Finish and inspect. Heat treatment, machining, cleaning, surface finishing, non-destructive testing, and meteorology close the loop. Advanced materials broaden performance but raise process control burden. Performance promise: lightweighting, heat resistance, corrosion resistance, strength, conductivity, biocompatibility, and durability. Process sensitivity: temperature, humidity, cure, pressure, powder quality, mixing, contamination, and handling can drive variation. Microelectronics manufacturing is defined by precision, yield, and contamination control. Process precision: tiny tolerances, clean environments, trace cases, photolithography, deposition, etch, and dust discipline matter. Yield learning: high volume data, defect maps, parametric tests, and equipment history drive rapid yield improvement. Battery manufacturing is a process control and scale up frontier. Yield sensitivity: small variation in moisture, coating, thickness, temperature, pressure, or contamination can affect performance. Safety and traceability: material lots, cell genealogy, formation data, test results, and handling history support containment and quality. Biomanufacturing shows how digital quality and compliance can coverage. Process understanding: critical parameters, cell culture conditions, yield drivers, sterility, and variability must be controlled. Digital records, electronic batch records, genealogy, deviations, kappa, and equipment status improve compliance evidence. Chapter 7 deals with quality, reliability, and traceability in digital operations. Quality 4 connects prevention, detection, and learning. Prevention: use control plans, process capability, mistake proofing, and parameter monitoring to prevent defects. Detection: use inline inspection, SPC, vision tests, and audit signals to detect abnormalities earlier. Traceability turns genealogy into operational risk management. Forward trace: identify where a material lot, component, or process condition ended up in finished goods. Backward trace: find the source materials, equipment, parameters, and events behind the quality concern. Closed loop corrective action prevents the same failure from reappearing. Contain quickly: stop shipment, isolate WIP, notify owners, and protect customers while the cause is investigated. Fix the system: Update the design, process, supplier, tooling, maintenance, training, control plan or software logic. Reliability centered maintenance links asset health to production risk. Criticality. Rank assets by safety, quality, throughput, service, environmental and repair time impact. Failure modes. Use FMEA, condition data, work history and operator observations to understand likely failures. Supplier quality becomes a real-time risk management system. Incoming signals, certificates, inspection results, delivery performance, deviations, material lots and audit findings. Risk scoring, prioritize suppliers and materials using severity, occurrence, detectability, capacity and recovery exposure. SPC and process capability still matter in digital plants. Connected data increases the need for clear control limits, sampling logic and interpretation discipline. Control charts track common costs and special cost variation so teams know when to investigate and when to stabilize. Capability, use CP, CPK, PP and PPK carefully to understand whether the process can meet specification reliably. Chapter 8 deals with supply chain planning and resilient manufacturing networks. Modern manufacturing needs synchronized planning horizons. Strategic horizon, network footprint, capacity, technology, roadmap, make by decisions and resilience posture. Tactical horizon, S&OP, demand shaping, supply planning, inventory, constraints and resource balancing. Digital supply networks sense risk earlier than linear supply chains. Risk sensing, monitor supplier events, port delays, weather, quality issues, shortages, demand shifts and geopolitical risk. Scenario planning, model alternate sourcing, substitutions, inventory positioning, capacity shifts and custom allocation. Inventory strategy shifts from buffer size to buffer intelligence. Differentiate buffers. Segment by demand variability, lead time, margin, service criticality, substitution risk and obsolescence. Use risk signals. Adjust safety stock based on supply reliability, logistics, disruption, quality risk and demand changes. Regionalization changes manufacturing footprint decisions. Cost trade-offs, labor, automation, freight, duties, incentives, energy, real estate, taxes and working capital. Risk trade-offs include geopolitical exposure, logistic disruption, supplier concentration, compliance and service continuity. Factory scheduling must be tightly coupled to materials and capacity. Schedules fail when they ignore component status, labor, tooling, maintenance windows and real equipment states. Material readiness. Link orders to component availability, incoming receipts, pulls, substitutions and line side inventory. Capacity realism. Model bottlenecks. Changeovers, labor skills, downtime maintenance, cleaning and qualification constraints. Execution feedback. Update schedules with actual progress, quality holds, scrap, rework and unplanned events. Warehouse and intra-logistics are part of the production system. Material presentation, kitting, sequencing, supermarkets, Kanban and point of use delivery reduce searching and line interruptions. Warehouse execution, WMS, scanners, inventory accuracy, lot control, cycle counts and location discipline protect flow. Integrated automation, conveyors, ASRS, AMRs and big technologies must connect to production needs. Chapter 9 deals with workforce skills and culture in modern manufacturing. The workforce model shifts from operators to problem solvers and technologists. Frontline teams. Operators use digital instructions, capture abnormalities, interpret signals, and participate in problem solving. Technical specialists control automation, data, quality, maintenance, and process engineers work in integrated product teams. Leaders, supervisors, and managers coach adoption, remove barriers, and align technology with operating routines. Skill strategy must combine digital, technical, and problem solving capability. Technical depth, process, maintenance, controls, quality, safety, materials, robotics, and equipment knowledge. Digital fluency include data interpretation, digital work instructions, analytics, cyber hygiene, automation interfaces, and AI assistance. Training must move from classroom events to a capability system. The goal is not attendance, it is demonstrated proficiency under real production conditions. Role-based paths define required skills, prerequisites, learning modules, practice tasks, and certification thresholds by role. Practice and feedback. Use simulators, digital work instructions, coaching, shadowing, and observed work to build skill. Change adoption. Frontline adoption depends on trust and visible usefulness. Start with pain points. Target searching, rework, unclear instructions, slow escalation, missing materials, and recurring downtime. Co-design work includes frontline users in workflow, screen, alert, and standard work design before scale up. Safety, ergonomics, and inclusion improve manufacturing performance. Design out strain. Addresses lift weight, reach, posture, repetition, visual demands, noise, heat, and traffic exposure. Standardized support includes using the fixtures, assists, clear instructions, and tools that accommodate varied worker needs. New manufacturing roles blend operations, data, and engineering. Manufacturing data engineer. He builds data pipelines, context models, dashboards, data products, and analytics deployment patterns. The automation product owner. He owns the robot, controls, and automation roadmaps across use cases, standards, and plant adoption. A learning culture makes digital tools compound over time. Psychological safety. Teams must be able to surface problems, stop escalation, and ask for help without blame. Standard routines. Daily management, Gemba walks, tier meetings, and a retrospective create a rhythm for learning. Chapter 10 deals with sustainability, energy, and circular manufacturing. Energy productivity is becoming a core manufacturing metric measured by process. Submeter major loads, link energy to production state, and identify base load, idle, and peak drivers. Improve operations, optimize compressed air, high voltage air compressor, ovens, motors, pumps, scheduling, warm-up, standby, and leak losses. Decarbonization starts with process, energy, and materials visibility. In scope 1 and 2, you may need to track the fuel, electricity, steam, refrigerants, and on-site generation by process, line, product, and time. Scope 3 includes inputs such as material composition, supplier data, logistics, packaging, and product use phase assumptions of affect footprint. Circular manufacturing needs design, recovery, and reverse logistics. Design for recovery. Use modularity, material leveling, repair access, disassembly, durability, and upgradability. Operate recovery flows. Inspect, grade, clean, repair, remanufacture, refurbish, recycle, or dispose based on condition and value. Waste reduction links lean, quality, and sustainability. Lean waste. It includes overproduction, waiting periods, transport, overprocessing, inventory motion, defects, and unused talent. Material waste includes scrap, yield loss, off-spec product, packaging, purge, trim, and expired materials. Water and resource stewardship are becoming site-level constraints. Site exposure, water stress, grid reliability, permitting, waste treatment, community impacts, and climate hazards. Operational levers include reuse, closed-loop systems, leak detection, chemical optimization, and process redesign. Product carbon data needs the same discipline as quality genealogy. Trace the inputs. Connect material origin, supplier factors, process route, energy source, logistics, and scrap to each product family. Calculate consistently. Use common methods, units, boundaries, allocation rules, and document assumptions across plants. Chapter 11 deals with governance and operating model for scale. Governance should connect value, risk, architecture, and adoption. Value governance. It prioritizes use cases by measurable losses, strategic relevance, scalability, and payback confidence. Architecture governance includes approving the standards for data integration, cyber, platforms, devices, and reusable reference designs. Use case portfolios should balance quick wins and platform bets. Quick wins target visible losses such as downtime, scrap, energy, searching, scheduling churn, and manual reporting. Scale the use cases. Prioritize problems repeated across many lines, assets, product families, or sites. Digital product teams reduce the handoff cost between functions. Product owner. He owns the user value, adoption, roadmap, prioritize, and the benefits for a digital manufacturing capability. Engineering SWOT combines process automation, controls data analytics, cyber, and application skills. Value realization must be designed before the pilot starts. Baseline the loss means quantify current downtime, scrap, labor, energy, yield, rework inventory, or service loss clearly. Assign ownership. Name the operational owner, financial validator, adoption lead, and sustainment owner yearly. Standards are the mechanism that lets plant scale without cloning. Common core. Define architecture, data model, security controls, naming, interfaces, and reporting conventions. Local fit, which means allowing variation for product, process, regulation, equipment, language, and site maturity where justified. Cyber resilience is an operating capability, not only a control checklist. Prepare asset inventory, network segmentation, backups, assess controls, vendor rules, and recovery procedures. Respond to plant-aware incident playbooks, roles, communication, containment decisions, and production safe actions. Vendor ecosystems should be managed for interoperability and leverage. Strategic partners. Use partners for platforms, automation, controls, integration, analytics, and support where scale matters. Open interfaces, which means protect the data access, integration rights, exportability, cyber requirements, and lifecycle support tabs. Chapter 12 deals with roadmap, metrics, and the future ready factory. Start with the maturity assessment that links capability to value. Value the baseline, which means quantify losses in downtime, scrap, labor, energy, throughput, inventory, service, safety, and quality. Capability baseline. Assess the data, systems, automation skills, cyber, process discipline, and governance maturity. Pilot to scale requires a deliberate industrialization path. A pilot proves feasibility, scaling proves repeatability, supportability, and measurable adoption. Prototype. Validate the problem, users, data, workflow, benefit hypothesis, and technical feasibility. Industrialize depends upon hardened security, support, documentation, training, reliability, integration, and operating procedures. Build the roadmap in 3 horizons, not one giant program. A practical roadmap sequence value foundations and operating model change in parallel, 0 to 6 months. Baseline losses. Choose priority use cases, establish governance, fix critical data gaps, improve yearly value. 6 to 18 months. Scale repeatable use cases, standardize architecture, train teams, and integrate benefits into daily management. A balanced scorecard keeps value, maturity, and risk visible. Business outcomes. OEE, yield, scrap, labor productivity, energy intensity, delivery, inventory, safety, and quality escapes. Capability maturity, which includes data coverage, connectivity, cyber posture, model adoption, skills, platform reuse, and standard adherence. A transformation risk register keeps the program honest. Data and integration risk, incomplete context, fragile interfaces, legacy constraints, and inconsistent master data can still scale. Adoption risk, workflow friction, weak training, poor trust, and unclear ownership can make tools unused. Reference architecture should evolve through capability waves. Wave 1, connect. Secure networks, data capture, asset hierarchy, core systems, integration, and visibility dashboards. Wave 2, optimize. Context models, analytics, predictive maintenance, quality loops, scheduling, and standard playbooks. Wave 3, adapt. Digital twins, AI agents, flexible automation, autonomous material flow, and network orchestration. The future-ready factory becomes an AI-assisted learning system. Sense continuously assets, products, materials, operators, environment, and logistics create a living operational signal. Decide faster. AI, analytics, standard work, and daily management convert signals into prioritized actions. Manufacturing playbooks must fit the process archetype. Discrete assembly, focus on fine balance, robotics, traceability, flexible work cells, material presentation, and quality at source. Process and batch, focus on recipes, parameters, yield energy, contamination, batch records, and process analytics. Engineer to order, focus on digital thread, configuration, project flow, supplier coordination, and skilled labor planning. Executives should make 5 explicit manufacturing choices. Where to compete? Choose the value pools, plants, product families, and network roles that matter most. What to standardize? Decide which platforms, data model, cyber controls, process, and rules must be common. How to scale? Commit funding, governance, talents, partners, benefit ownership, and adoption cadence. The first 90 days should create focus, facts, and momentum. Days 1 to 30. Baseline value losses. Choose priority plans, confirm sponsors, and form the cross-functional core team. Days 31 to 60. Assess data readiness, select first use cases, design adoption workflows, and define benefit measures. Days 61 to 90, launch pilots, establish governance, publish standards, and prepare the first scale decision gate. The recommendation for modern manufacturing is build an adaptive manufacturing system, not a technology showcase. Prioritize the value pools that matter, build reusable digital and automation foundation, redesign daily work, and scale only what changes performance in the plant work. Thank you so much.